going to be speaking about three-dimensional oblique shockwave boundary layer interactions. I apologize if some of the quality is a bit low because I'm connecting with the Zoom. Okay, so in practice, oblique SBLIs occur in many supersonic flow fields. For example, in mixed compression jet intakes, such as on the Concorde, where we have a rectangular intake. We then get oblique SBLIs occurring on the floor and on the ceiling. Also in transonic compressor cascades. And in practice, these often occur near to sidewalls. So, for example, in the rectangular intake, we have these sidewalls present, and this results in a three-dimensional interaction. Okay, so to observe this in our wind tunnel, we're running at Mach 2.5, and we use an 8-degree wedge to produce an incident shock wave that then interacts with this turbulent boundary layer to produce an oblique SBLI. So let's look at the Schlieren of that interaction. And we see a sort of standard separated interaction with the incident shock, the separation shock, and the reattachment shock. Let's look at an oil flow visualization. So we get this three-dimensional separation where we have this primary separation in the center, and we have separations in the streamwise corners of the tunnel. Okay, so why do we get this three-dimensional separation? Well, it's related to the presence of the sidewalls. So we get a sidewall boundary layer that's meeting a boundary layer on the floor, and this results in a thick corner boundary layer. This has a lot of low flow momentum and therefore separates readily. In fact, it tends to separate upstream of the primary interaction, the primary separation. And these corner separations generate waves, so compression waves, which may form a shock wave, and expansion waves. These waves interact with the primary separation, and this results in this three-dimensionality. We also get attached flow channels on the sides of the separation. Okay, so to explore corner effects in more detail, we use artificial corner separations. So in particular, we use these corner cones, these conical bodies, which we place in the streamwise corners, and this gives us a controlled corner effect. If we look at the pressure distribution without an incident shock wave, we first get an initial pressure rise, and so I've indicated that with these compression waves, and then that's followed by a pressure drop through expansion waves, which emanate from the apex of the cones. If we look at the centerline pressure distribution, so plotting pressure versus streamwise coordinates, we see that we first get this gentle pressure rise through these compression waves, and then we get a pressure drop through the expansion waves. To give a sense of scale of how strong these corner waves are, that is the pressure rise for the reflecting interaction. So for this interaction at Mach 2.5 with an 8-degree deflection, that's the pressure rise that we get overall. The compression waves are increasing the pressure to about 18% of that, and the expansion waves are then dropping the pressure all the way down to about below 9% of the upstream pressure. Just to give you a sense of how strong these waves are. Okay, so we then move the corner cones upstream and downstream relative to the interaction so that we can see what a varying corner effect has on the separation. Okay, so let's start by looking at some sample flow fields. So starting with the cones quite far downstream of the interaction. So I'm going to plot for a series of cone positions the separation length measured along the center line. That's non-dimensionalized by the upstream displacement thickness, and this is the cone position. So currently we're in cone position 2, and That is the baseline separation length for reference. So in this current position, we have a slightly increased separation length compared to the baseline case. And I've also drawn on the approximate position of these waves to get an idea of where they're interacting. Okay, so we move the currents upstream in 10 millimeter increments, and I'll just show a few key cases. So moving quite a bit further upstream in position 6, we see that the separation length has now increased quite markedly compared to the baseline case. It's more than double already. And in this case, we have some compression waves arriving over the interaction. If we then move the currents further upstream, we get to this case where we get the maximum separation length. And in this case, we have these compression waves which are arriving mostly over the interaction itself. Moving the currents further forward again, we get to a case, well, now the separation length starts to drop, and in fact, it drops below the baseline separation length. Moving them further forward, we get to a case where we have a very small separation length. I mean, it's like almost non-existent compared to the baseline case. But in this case, we see that we have expansion waves arriving over the interaction. Okay, so that's the minimum separation length. All right, and then this is the most extreme case with the corner cones far upstream, and now the expansion waves arrive upstream of the interaction. Okay, so these are all the different cases that we considered. So 19 different positions. And we see we get a very large variation in the separation length. So more than double the baseline and going down to almost having no separation at all. Okay, so how are these corner waves producing this effect? Okay, so I want to look at the separation length versus pressure rise, starting at the center line. Okay, so this is the baseline case, and we're going to look along the center line, and we're interested in how the pressure from the separation point to the reattachment point relates to the separation length in the center. Okay, so we're going to plot separation length versus that pressure rise, and this is where the baseline case sits. And then if I include all these different 19 different cases, that's what we get. Okay, so we get a clear correlation between the separation length and the pressure rise along the center line. You can draw a fit through that. And we see that the corner effect is as I mentioned, in the extreme, more than doubling the separation length, and at the minimum, it's almost eliminating that separation. So there's a strong corner effect. If we look at the case where we had this increased separation length, so this was the case with the maximum separation length, and comparing that to the baseline separation. In this case, as I briefly mentioned, we have compression waves which are arriving over the interaction, okay? Whereas in the smallest separation length case, we had expansion waves arriving over the interaction. Okay, so it's important what kind of waves you have arriving over your interaction length. So physically, what's going on here? Well, if we look at a schematic of a two-dimensional interaction, where we have the incident shock wave, the separation shock, of course, this is the separation bubble. We also have these expansion waves and this reattachment shock. But what I want to focus on is this shear layer. Okay, so the shear layer accelerates from the separation point, and it gains momentum by shear stress from the outer flow. And in fact, it must gain enough momentum to overcome the pressure rise at reattachment. So it's got to gain enough momentum to overcome that pressure rise. And therefore, we need a certain length in order for that momentum to be gained. And thus, the separation length is somehow proportional to that pressure rise. Okay, so that's, loosely speaking, the relationship between separation length and pressure rise. When we have compression waves arriving over the interaction, well, those compression waves act to decelerate the shear layer. This means that more momentum is required in order to overcome that pressure rise through to reattachment. And this means that we need an increased separation length. Okay, and that's what we see. We see an increased separation length. When we have expansion waves arriving, on the other hand, they act to accelerate the shear layer. And this means that less momentum is required and we get a decreased separation length. Okay. So that tells us something about how the separation length changes with these corner waves. But we also saw that we have complicated separation shapes developing for varying corner effects. Okay, so we want to try and explain how that works. And to do that, we'll do a similar analysis we did before along the center line, but now we'll also consider taking strips at off-center locations. So we take a whole series of streamwise strips, and along each of those strips, we do the same thing where we look at the difference in pressure from separation to reattachment and consider how the separation length at that point relates to that pressure rise. So this was the centerline plot of separation length versus pressure rise. If we now include all the different cases and all the different strips for those cases, that's what we get. Okay. So we still see a strong correlation between separation length and pressure rise, even at off-center locations. We can again put a fit through that. And if we include the error that's associated with the measurements from pressure-sensitive paint, well, we see that actually there's some scatter that falls outside of that uncertainty, okay? So this indicates that there's some secondary effect that we're not yet capturing. Now, maybe this is due to three-dimensionality, but it turns out that it has something to do with waves that are arriving upstream of the interaction. So showing this maximum separation length case again, if we look at one of these off-center strips, we can plot the pressure along that strip, along the streamwise direction. And I've also included the pressure distribution along the center line that we got for just the cones without the incident shock, which I showed earlier on. So over the interaction, we have this pressure rise, which I've been discussing. Now we can see from the corner wave, the corner pressure, corner cone pressure, that in this region, there's an increase in pressure that indicates that we have compression waves arriving. So this is what I've been arguing, that these compression waves are driving an increase in pressure. But okay, so that makes some sense, but we also need to consider what's happening upstream of the separation, because we have all of these pressure waves which are arriving upstream, and we need to see if it has some effect on the separation length. And this is particularly true off-center. So the further we are away from the center, the more we have pressure waves that arrive upstream of the separation. Okay, so what is this? Is there some dependency? Well, to consider that, we correlate separation length to both of these pressure rises. Now, I'm not going to go into too much detail on that because it's you get a you have two parameters, and you have some kind of surface that you're trying to fit. But from that, you can derive a corrected pressure, which accounts for both the pressures arriving upstream and the pressures over the interaction. So this is just an empirical fit that we get from that. And then if we now compare the separation length to this corrected pressure, this is what we get. Okay, so we get a much better collapse of the data. And if we include the error, we see that now the data seems to fit more or less within that uncertainty. So we've kind of captured the effects that we can within the measurement uncertainty that we have. Okay, so right, so that's just an empirical fit. But what does it physically mean? Well, we can't be sure yet, but I would propose the following. So waves that arrive upstream of the interaction, we expect that they should have some effect on the incoming boundary layer. And in particular, they may vary the the thickness of that boundary layer and the displacement thickness. And we know from Suver et al. In 2013 that for a two-dimensional interaction, the separation length scales with the displacement thickness. And so we expect that these upstream waves are having some effect on the separation length by changing the incoming displacement thickness. Okay, so what does this tell us about the separation shape and how it's affected by corner waves? Well, we've seen that that the separation length at any point seems to only depend on pressures within that strip. So there's this quasi two-dimensional relationship between separation length and the pressures along that streamwise strip. So that's quite surprising, and it allows us to kind of model how corner waves change the shape of the interaction. Okay, so we've seen how corner waves can vastly change the length of the separation, and also how they create complicated separation shapes. But what does this tell us about what we can do about separation? Is there some kind of flow control perspective we can get from this? Okay, well, we've seen that pressure waves have a very strong control effect. In our case, we had relatively weak waves causing a very large change in separation length. So one method that we propose is that what if instead of generating waves in the corners, we generate waves on the surface? So we could do this using a surface bump. So that creates initially some compression waves or a shock, followed by some expansion waves, and then some more compression waves, which may be a shock wave, joined to become a shock wave. So the idea with this is that if we place this bump just right, then the expansion fan that emanates from the top of that bump will be formed at the exact point where the incident shock arrives. And that expansion fan can act to reduce the adverse pressure gradient due to that shock. And so the flow that's going over this bump is then not facing this full adverse pressure gradient of the incident shock wave. And in this way, it can potentially reduce or eliminate separation. Well, hopefully. Okay, so does this work in practice? So we decided to just start by creating a bump that was shaped like the separation bubble itself, because we didn't know what would be the optimal shape. So we decided that was a place to start. So we just literally took the separation bubble shape, the time average bubble shape, and created a bump that matches that. But we did this in 3 dimensions. So we took from the oil flow, we had an idea of the 3-dimensionality of that separation, and we created a 3-dimensional bump, which we then 3D printed and stuck on the surface. So as Alessandro pointed out earlier, this has become a TEAMAero collaboration. The first experiments we did some experiments in Cambridge, and then I went to TU Delft and worked with Jane, who's working on some other shock control bump geometries. And we did this thing where we looked at the baseline separation, created this bump shape, which you can't see very clearly there. But I'm just going to show some brief results that we got from that. I'm not going to go into all the results that we have, not in this presentation at least. What I'm going to show here is just some oil flow visualization. So this is a video that I'll now play. So the flow is from left to right. I'll just let this play now. Okay. Baseline is not there. Right, so in the baseline, we can quite clearly see this reversed flow, and we very clearly see the separated region. And that's the shape that we used for the bump. If we look at the bump case, if we follow those streamlines, we see that they're actually remaining attached over the bump. So if we look at that a bit more closely, extracting that image and looking at a top-down view by correcting for perspective. So these are the streamlines that we're looking at, and we can see that they are in fact remaining attached. There is some flow of separation that occurs on the side of the bump, but overall we have this result that the bump pretty much eliminates the separation, which is quite exciting. So how does this work? Well, I've kind of already preempted this a little bit, but essentially, well, what we need to think about is what is the incoming boundary layer experiencing as it goes over the bump. So it initially experiences a compression corner at the leading edge of the bump, and then it experiences this incident shock. So how does this boundary layer remain attached? Well, because the shape of the bump is the same as the separation bubble, we know that this compression corner angle must be less than what would be required to create a separation, because if that were not the case, you would, in the uncontrolled interaction, must have a different shape. You'd have to have a different angle of that bump, of the bubble. And then when the incident shock meets the boundary layer, we have these expansion waves. And in fact, because we've used the shape of the separation bubble, those expansion fans should be of the same strength, or approximately the same strength. And in the uncontrolled interaction, those expansion waves act to reduce the adverse pressure gradients to just the point where this flow is able to kind of remain attached over the separation bubble. And so this is how we propose that this is working, but we still need to do some more exploring into the physics of this. Okay. I won't go into too much detail on this, but we also have been looking at the unsteadiness of this interaction. So in particular, we're interested in the low frequency breathing mode of the separation bubble. And so we took some high speed shadow graph of the interaction and extracted the region around the shock foot. And this is the power spectral density with the non-dimensional frequency on the vertical axis. And we quite clearly see this low frequency mode in the baseline case. But when we use the bump, it essentially eliminated that low frequency breathing. Okay, so it's quite promising results with these control bumps so far. As Alessandro was showing us earlier, he's been working on some quasi two-dimensional DNS, which is looking very exciting. I also went to TU Berlin when I was working with Cosimo, and we were trying to apply piezofoil measurements to take unsteady pressures around these bumps. So there'll be more results upcoming, I hope. So in conclusion, pressure waves arriving over the interaction are significant. Relatively weak waves can cause a very large change in separation length. The separation shape can be understood based on this quasi two-dimensional relationship between separation length and pressure rise, where the most important thing are the waves arriving over the interaction, but there's also some secondary effect of upstream pressure waves. In terms of flow control, we developed a control bump, which was able to generate waves which could eliminate the separation. Thank you very much.